So, good afternoon. So, what topics did we discuss in the last lecture? You remember only diagram from last lecture? So, first we introduced what are called Bellman optimality equations, right? So, what are Bellman optimality equations? Like, those are useful for finding the optimal policy, right? The optimal value function will satisfy these Bellman optimality equations, right? And then after that, we discussed some diagram called backup diagram, right? And then we have also seen an algorithm called policy iteration algorithm, right? And then we have also showed, we also discussed why policy iteration works by stating a theorem called what? Policy improvement theorem, right? The policy iteration works because of this theorem, right? So in today's class, what we'll discuss is we'll discuss another algorithm called value iteration, and we'll also, like in the policy iteration, if you remember, there are two steps. What are those two steps? You start with some arbitrary policy pi naught, and then you evaluate that policy pi naught, then you improve that policy, right? So there is policy evaluation step and then policy improvement step. In last class, we have shown that the policy improvement step will actually improve the policy, right? We haven't discussed how are we going to evaluate the policy, right? We just said that you can take the inverse of some matrix, which like you write the Bellman expectation equation, and from that you just write it as Ax equal to B form and find the policy value of the policy. But taking the inverse is a complex operation which have too many states and actions. So we'll discuss some way to evaluate the policy. Like instead of doing an inverse of a matrix, we'll try to look at some other way to evaluate the policy, and we'll see why. We'll propose a simple way to evaluate the policy, and then we'll discuss why that simple way will work. Okay, so that is what we'll do today. So, what is Bellman optimality equation? Do you remember? So, Bellman expectation equations. Do you remember? So, what is Bellman expectation equations? The value function of a policy pi in a state S is equal to what? The immediate reward that you get for playing policy pi in that state S plus gamma times the remaining return. The remaining return will be some v pi of S dash, and we don't know which state we'll go into, so we'll sum over all possible states and just multiply with the respective probabilities of going to that state S dash from state S when you act according to policy pi. So this is the Bellman expectation equation. And the Bellman optimality equation, how did we get? So we got it from this understanding, right? Let's say someone gives you a Q star of S comma A for all the actions and states. If we are asked to find what is the V star of S, how can we find? V star of S equal to what? in terms of Q star of S comma A? Q star of S comma A is saying that if you take action A right now, and from the next step you follow policy, you follow the optimal policy, you behave in the best possible way. From the next step, you will get the Q star of S comma A. So if you want V star of S, you want to do optimally even in the current step. So what should we do? Like this is what we can do, right? Even take this current step optimally. Okay, this is the best value that you can get, right? So we just expanded this equation to get the Bellman optimality equations. So if you write Q star in terms of V star, what will we get? Like Q star of S comma A will be like the immediate reward for taking action A right now, which is what? What is the immediate reward that you get for taking action A in status? This is the immediate reward plus the remaining return, which is what? Uh, V star of S dash into PASS dash, right? You're taking action A, right? So you took action A, what is the probability that you'll go to S dash? So this is what we defined as the Bellman optimality equation, right? So this is about the Bellman optimality equation, and backup diagrams are anyway somewhat easier, so I'll not go into details of that again. And the policy iteration algorithm, maybe I'll just write one more time. So what is policy iteration algorithm? You start with some arbitrary policy pi naught, and then you evaluate that policy pi naught. Then what will we get? We get v pi naught, let's say, or q pi naught, whatever you want to evaluate. And then what do? We improve this policy pi naught. How are we going to improve this policy? Do you remember how are we going to improve a policy pi naught? So you take pi 1 equal to, right? This is how we improve the policy, right? You just evaluate your policy pi naught, then you behave greedily in the sense that you just, in some status, you take the argument which will maximize that. So in every state, you look at which action will give you the maximum value of q pi naught of S comma A and take that action. Okay. So we have shown, what did we show in yesterday's class about pi 1? If you take pi 1 like this, what did we show? Yeah, v pi 1 is greater than or equal to v pi naught. And we also understood that like if pi t plus 1 equal to pi t, then it implies that pi t is an optimal policy, right? Why is that? Because that will satisfy the Bellman optimality equation if you substitute this, right? Because what is Bellman optimality equation? This is Bellman optimality equation, right? So if pi t plus 1 is equal to pi t, then that means you can show that it will satisfy the Bellman optimality equation. Okay. So I think some of you are a little bit confused about the proof that I've given yesterday. So maybe I'll try to explain that again. So right now, if from this expression alone, uh, we cannot see that v pi 1 is greater than or equal to v pi naught, right? Because what if they're telling you take in some status, instead of taking action according to pi naught, you take an action like this, right? So what does that mean? So if I look at mm, so if I want to value, if I want to behave according to pi naught, all like even that step, what is the value that I'll get? Q pi naught of s comma pi naught of s. This is what is the value of pi naught, right? You just behave according to, afterwards you also behave according to pi naught. This is the value of policy pi naught, right? This much everyone is clear, right? The value of a policy pi naught is this, correct? Now what did we do? We have we are telling that so you are looking like this. You have, let's say there are three actions possible in a state S. So these are three